How you doing, guys? Welcome to the video. We're looking today fundamental applied maths. This is just a continuation of the last video, which was exercise 11D. I said I'd do 1, 4 and 5, so I only did 1, so I'm doing 4 and 5 in this video. Starting with question 4. The question is this: a hollow sphere has center C and radius R. A small marble Q rests at the lowest point inside the smooth sphere. It's then projected horizontally with initial speed √7/2gr. Find the angle which the line CQ makes with the downward vertical. That's this angle here as the line CQ as the marble moves around. At the moment when the marble moves away from the inside surface of the sphere. So as the marble moves up, at some stage it's going to lose contact with the sphere and it's going to maybe fall out this way. Through what vertical distance has the marble traveled at this point? What's its height? Okay, so let's look at a few things in this question. Initially, we've got ourselves an initial velocity of root. Those square roots are handy because you always square your initial velocity, 7/2gr. We're going to be interested in the height for a number of places in a number of parts of this question, so I'll have an examination of that in just a second. Here's our primary tool, I suppose, in this problem, is that as the marble moves up, when it moves around here, the point at which it loses contact, so if you can imagine what the normal force needed to keep it moving in a circle, as it slows down, even as it gets here, it needs less and less inwards force from the thing to keep on moving in a circle. So the faster it's moving, the more the hollow sphere, as it were, has to push against it. And at some point up here, that normal force is going to be completely reduced to 0 and the marble is going to fall away from the edge of the sphere. So that's the point we're interested in, and our condition is that it loses contact when the normal force equals 0. The height of the marble is also something we're going to want to know. We know this height is r. That length is also the radius r. So looking at this right angle triangle here, this distance from here to here is going to be r, that's the adjacent side, so it's r cos theta. Okay, so the height at which the marble is at any instant, this height here, is the radius minus r cos theta, and that's a very common equation. You'll see that crop up in a lot of these problems. One of the things about it is that cos theta, when that angle, as the line comes, or as the marble moves around here, that angle is going to become obtuse. Well, the cos of an obtuse angle is always negative. So you're going to get r minus minus. So you get r plus some fraction of the radius instead of r minus some fraction of the radius. So that equation works the whole way through the motion of the circle. So once we have that, we can go to our usual conservation of energy, which says half m times our initial velocity squared. I'm just going to square it straight away, so 7/2gr plus our initial potential energy at the lowest point is 0 is the same as a half mv squared, and v squared is what we're always trying to get, plus mg times some height, and we know now an expression for the height, so we can plug that in a second. So straight away you've got a common factor of m through each of those expressions. So what do we get? 7gr/4 equals v squared over 2 plus g times r minus r cos theta. Okay, and it'll be useful to get rid of our fractions. Well, at least get rid of that 2. Okay, so we'll do that, and actually we'll do that in a second. We'll start moving things first. That is going to be v squared over 2 plus gr minus gr cos theta. So when we move them over to the other side, we get 7gr/4 minus gr plus gr cos theta equals v squared over 2. Okay, well this can be thought of as 4gr/4, and we're going to say 7gr/4 minus 4gr/4 is 3gr/4 plus gr cos theta is v squared over 2. Multiplying through by that 2 is going to give us 6gr over 4 plus 2gr cos theta is v squared. So that's what we're going to be working with from conservation of energy. Our second equation is that our inward forces is what causes our centripetal force. That's what allows us to move in a circle. Okay, well, one of our inward forces is that normal force, the fact that the marble resting here is experiencing a reacting force from the hollow sphere. The other force acting is weight, which acts downwards, but we'll have to resolve that into a component along this direction and another component in that direction. Okay, well, that angle theta crops up down here again, and if you ever did this in your work, I'd give that to you, but I'm going to do it here for the sake of the video. We're going to resolve that mg, that is the adjacent side, so it's mg cos theta, and you'll see that mg cos theta come up a lot of the time when you resolve the weight. It's in the opposite direction, it's in the outwards direction, so that's a negative force here, mg cos theta, and that equals our centripetal force, which is mv squared over r. Okay, we have an expression up here for v squared, so we'll sub that in. Our next page is going to say n minus mg cos theta, all I'm doing is copying here, equals m over r, okay, m over r times, instead of v squared now, I've got 6gr over 4 plus 2gr cos theta. Okay, and radius is common to the inner terms in the bracket, and you're dividing by radius in the outside. So we'll cancel radius, and we'll tidy that up. We say n minus mg cos theta equals 6 over 4 is 3 over 2. So we get 3mg over 2 plus 2mg cos theta. Okay, now if you remember at the start of the question, at the point it loses contact, which is what we're looking for, the normal force is going to be 0. So let equals 0 because we've lost contact here with the surface of the sphere. Okay, and our equation now becomes 0 minus mg cos theta equals 3mg over 2 plus 2mg cos theta. And every term there has an mg in it. So what we're saying here is that at that point where n equals 0, what's the angle? That's what we're trying to find. Now, if we find we don't have a solution here, we've either done our maths wrong, or the normal force is never 0. Okay, and that can happen if you're moving fast enough. You'll get the marble to go all the way around. If you ever owned a Scalextric kit as a kid, if you've ever been on a roller coaster with a loop-the-loop on it, or if you ever watched a motorcyclist riding, I think it's called a wall of death, where they flip entirely upside down. The speed, if you're moving fast enough, you can maintain contact with the outside part of the sphere the whole way around. You'll always have that normal force greater than 0. So we've been told it loses contact, so hopefully we have a solution to this. To minus cos theta is 3 over 2 plus 2 cos theta. So move that over, you get minus cos theta minus 2 cos theta is minus 3 cos theta is 3 over 2. And cos theta then is minus 1 over 2. Okay, when you divide through by 3 and divide through by minus 1. Okay, so what's the inverse cos of minus a half? Well, it's a negative, which means we've got an obtuse angle, which is kind of what we expected, that we'd lose contact somewhere beyond our 90-degree point. And the inverse cos of a half, I think, is 120. Oh, sorry, of minus a half. So 120 degrees. So they said the angle CQ makes with the downward vertical at the moment when the marble moves away from the inside surface. Done. Through what vertical distance has the marble traveled at this point? Okay, so how high has it gotten? Well, we had an expression earlier for h. So that's this expression. Excuse me. Here, r minus r cos theta. So we're going to be giving our answer in terms of r. H equals r minus r cos theta, and cos theta we've seen is minus a half, so it's r minus r times minus a half. Okay, so we get r plus a half r, which is 3r over 2. Okay, there's question 4. Question 5 says a small bead of mass m is threaded on a smooth circular wire of radius a, fixed with its plane vertical. The bead is projected from the lowest point in the wire with speed u. Show that the reaction between the bead and the wire when the radius to the bead makes an angle of 60 degrees. The downward vertical is this mess here. Okay, so let's sketch up what we're looking at. Here's our circle. Okay, we've got our little bead threaded down here, and we're projecting it with some initial speed u. So it gets around to a point that is 60 degrees. We want to examine what the reacting force is. So at that point, what is our height? Well, our height is going to be our usual. They said A is the radius this time. So that's A as well. And our little triangle that we drew last time still holds. Sorry, I'm getting a bit crowded here, but that distance there is A cos, between here and here, A cos theta, A cos 60. So H is going to be A minus A cos 60, which is the same as R minus R cos theta that we've seen before. A minus A cos of 60 is 1/2. So A over 2 is the height that we're at. Okay, let me write that bigger, A over 2. So there's our height. Conservation of energy is where we'll go next. So conservation of energy says 1/2 mu squared plus, we're at the lowest point, so our potential energy at the start is 0, equals 1/2 mv squared plus mg, and our height now is A over 2. Okay, so straight away you've got it divided by 2 in each term, and you've got an m in each term. So that gives us u squared equals v squared plus ga. And v squared is what we're always looking for. That's going to be u squared minus ga. Okay, next up, forces in are what cause the centripetal force. Okay, well, our inward force here is the reacting force that we're being asked about, or the normal force, or whatever you want to call it. We've also got our usual weight acting downwards. Okay, and I'm going to resolve that up here. So weight acts downwards, and we want to resolve it into components along the radius of the circle. So along here, and perpendicular to the radius of the circle. Well, that angle 60 is going to crop up again down here as 60. So that's 60, and this is mg cos 60, which is mg cos 60 is 1/2, so mg over 2. This bit, as usual, mg sine 60, but we don't really use it. So our inward force is the reacting force on the wire, or at the wire. That weight is an outward force, so we say minus mg over 2 equals our centripetal force is mv squared over r, our radius, sorry, which this time is a. So that's going to be m over A times u squared minus GA. Okay, so we're trying to get a reacting force, so let's get it by itself. Reacting force equals m over A times u squared minus GA. That moves over and becomes plus mg over 2. So let's multiply this all out and see what we get. We get mu squared over A minus mga, over A, plus mg over 2. So A's cancel, top and bottom of this fraction. That says minus 1 mg plus a half mg, so that's minus a half mg. So we're left with mu squared over A minus mg over 2. Okay, another way to look at that is put a 2 top and bottom here, plus 1 minus 2, you're left with minus mg over 2. Well, if we take a common factor of m out of there, m times u squared over A minus g over 2, we get the mess that they asked us for in question 5. Okay, so I'd encourage you to give the other questions this chapter a go. I might try and post some videos of exam questions as well. Keep an eye out for them. Okay, bye-bye.